Hello students and welcome to the lecture. So students, as you can see here that basically in this lecture we are going to start with our new topic, that is the modern physics. Okay, we will talk about the concepts that come under the term of modern physics. What are their implications, definition, applications, uses and other related facts that are connected to them. This is going to be our part 1. Okay. In this lecture, basically, we will talk about the atoms and nuclei, Thomson model of atom, Rutherford's atom model, discovery of atomic nucleus, limitations of Rutherford atom model, Bohr model of hydrogen atom, De-Brogile, explanation of Bohr's second postulate of quantization, limitations of Bohr's theory, excitation and ionization potential, some important facts about atoms, nuclear forces, nature of nuclear force. Nuclear stability depends on many factors. We will see these factors. Radioactivity. So these all points are going to be the discussing point for us for this particular lecture. So let's see them again, starting with the atoms and nuclei, then Thomson model of atom, Rutherford atoms model, that is also known as the discovery of atomic nucleus, limitations of Rutherford atomic model, Bohr model of hydrogen atom, De-Broglie, De-Brogile explanation of Bohr's second postulate of quantization. What are the limitations of Bohr's theory? Excitations and ionization potential. Some important facts about atoms. What do you mean by the nuclear forces? Nature of nuclear force. Nuclear stability depends on which factors, and radioactivity. Okay, but before starting this lecture, as usual, we have the small disclaimer over here that we are required to understand first before we proceed further. Disclaimer is goes like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now let's first talk about the atoms and nuclei. What do we mean by this? So basically the structure of matter, that ever what we see around us, like the solid, liquid and gas, whatever things you are seeing around us, these all are the matter. Okay, like if we talk about it, so let me tell you one thing. Basically, generally we considered only the three forms of matter: solid form, liquid form, gaseous form. Okay, but scientifically there are the four forms. Okay, sorry, five forms, not four. Even five forms are there, not even four. Okay, after gases there are the you can say superionized gas and the Bose-Einstein. There was another state. So 4 and 5 states are also there, but these states are derived states. These are not the obvious states. So whenever we talk about matter, generally we consider only the three states, starting with the solid, then liquid, then gaseous. Got it? So basically, the structure of matter that shapes the world around us has been a subject of study since long. Like since starting, we have the curiosity to know about like why some things are solid, why some things are liquid, why some things are gaseous, and how they change their state of matter. Like if you burn the solid thing, it will transform into the liquid. If you burn the liquid thing, that will transfer to the gas. If you compress the gas, that will transfer to liquid. If you freeze the liquid, that will transfer to the gas. Sorry, that will transfer to the solid, ice cube. Okay, and even you could directly transfer the solid into gas, okay, and gas into solid. So these things were basically the point of curiosity for us to learn about them, like how these things are happening actually. The first contribution in this actually come from Dalton, who postulated the matter is made of atoms which are actually immiscible. J.J. Thomson, secondly, proposed a structure of the atom which are modified by Rutherford and later by Niels Bohr. The phenomenon of radioactivity has probably played the most significant role in the development of both the atomic and nuclear physics. So we could say first Dalton was the person who gave the contribution. Then J.J. Thomson, he tried to give the structure of the atom. Later on, this structure was got modified by Rutherford and then Niels Bohr. Okay, but the phenomenon of radioactivity actually contributed in the development of both the atomic and the nuclear physics. So that's how the things got actually started. So now let's have a talk on Thomson model of atom. So according to the Thomson's model, every atom consists of positively charged sphere of radius of the order of 10 power minus 10 meter, in which entire mass and positive charge of the atom are uniformly distributed. Okay, so first thing is, what do you mean by the atom? Okay, that is the first thing. So while we were discovering about the things like why some things are solid, liquid, gaseous, how the state of matter is getting changed, so in search of that we found that everything is actually made of atom except the living things. Living things actually made up of cells, but non-living things actually made up of atoms. Solid, liquid, gas, everything having atoms. After proposing that the atoms are the most fundamental unit of matter for solid, for liquid or gas, thereafter we tried to find out the structure, like how does the atom look like, because it is minute, invisible by the naked eyes, and they are you can say very small thing to be seen by the naked eye. Okay, so that is why different people, different scientists try to predict a different model of atom, or you can say different model or structure of atom, like maybe the atom look like this. Similarly, attempt did by Thomson. J.J. Thomson said that actually the atom is consisting of a positively charged sphere of radius of order of 10 power minus 10 m, in which entire mass and positive charge of the atom uniformly distributed. So he said, suppose this is the atom and the atom is actually having the positively charged ground. Okay, for example, and the entire mass and positive charge is actually uniformly distributed throughout the sphere. But later on, it was found that the Thomson atomic model having some kind of limitations and drawbacks. So what were these? Let's see. First, it could not explain the origin of spectral series of hydrogen and other atoms observed experimentally. So we could say the theory that was formulated by Thomson model was effective up to some limit, but when it got exposed to the spectral series of hydrogen and other atoms, it got failed. It was unable to explain them. So first limitation is this. Thereafter, it could not explain large angle scattering of particles from thin metal foils as observed by the Rutherford. So these two were main limitations of Thomson atomic model. The essential feature of Rutherford. Now we are talking about Rutherford's atomic model, because we know J.J. Thomson first gave the atomic model. Later on, it got modified by Rutherford and Niels Bohr. So first Rutherford will come. Rutherford's atomic model, that is also known for discovery of atomic nucleus. So let's have a talk on this. The essential features of Rutherford's nuclear model of atom, or which is also known as planetary model of the atom, are as follows. First, he said every atom consisting of a tiny central core, which we call the atomic nucleus, in which the entire positive charge and almost entire mass of the atom are concentrated. So he said, suppose this sphere is atom. So at the center of the sphere, there will be an atomic nucleus. Inside the nucleus, there will be a positive charge, and almost the entire mass of the atom will be concentrated in the center. The size of nucleus is of the order of 10 power minus 15 meter, which is very small as compared to the size of the atom, which is of the order of 10 power minus 10 meter. So Rutherford decreased the size of the nucleus. Okay. He said it is nearly about 10 power minus 15 meter, and atomic size was 10 power minus 10 meter. So nuclear is smaller in size in comparison with the atom. The atomic nucleus is actually surrounded by a certain number of electrons. Here you can say these. So these electrons actually surrounded the nucleus. Here you can see also. As atom on the whole is actually electrically neutral, the total negative charge of electrons surrounding the nucleus is actually equal to total positive charge on the nucleus, which means that the positive charge equals to the negative charge. No one is greater. Atom neither positive nor negative. That's why it is electrically neutral. Okay. These electrons revolve around the nucleus in various circular orbit. Okay, as do the planets around the sun. So here you can say, suppose this is the sun, these are the planets. We know the planets revolve around the sun. Similar thing Rutherford said about the atom. Nucleus is at the center and the electrons revolving around the nucleus, like the sun. The centripetal force required by electron for revolution is provided by the electrostatic force of attraction between the electrons and the nucleus. Centripetal force is actually the force that forces the outer thing towards the center of the circle. So that's why the thing is in the revolution. So he said the centripetal force that is required by the electron to revolve around the nucleus is actually provided by the electrostatic force of attraction that is lies between the electrons and the nucleus, between them. Okay. In Rutherford atomic model, now we talk about the limitations. What are the drawbacks and limitations of Rutherford atomic model? Why it got failed? In Rutherford atomic model, an electron is actually revolving around the nucleus and constantly experiencing a centripetal force. Like he said, there is a nucleus in the center and the electrons actually revolving around it again and again, again and again. Okay, by the virtue of centripetal force. That is what he said, right? Therefore, the electron having an accelerated motion. Okay, because if continuously it got attracted towards the center of the atom, so it will be accelerated. It will start moving fastly. According to the classical electromagnetic theory, the electron must radiate energy in the form of electromagnetic waves while in the revolution or in the motion. As the revolving electron will lose the energy continuously because it is in a motion constantly, it must spiral inwards and eventually fall into the nucleus. So what is happening here? Suppose if the electron is actually revolving around the nucleus on the continuous basis. So while doing a revolution, it will release the electromagnetic waves, which will discharge its energy, and that will happen on continuous basis because it is in continuous motion. And then what will happen? Eventually, the electron will become out of energy, and when it will become out of energy, it simply goes to the center and get collapse. Okay. As matter is stable, we cannot expect the atoms to collapse. But in reality, what is actually happening? The electrons not going to collapse with the nucleus. So if we apply this electromagnetic theory, or we could say the classical electromagnetic theory, to that particular incident that we are experiencing because of the Rutherford atomic model, this should be happen, but this is not happening, right? Why? Because we could not expect the atoms to collapse, and that was one of the major limitation of Rutherford atomic model. Like on the one hand, Rutherford said that the electrons revolving around the nucleus like the planets revolve around the sun, but While revolving, the electromagnetic waves must be radiated by the electrons, and if it is happening, the electrons will lose the energy while revolution. And when they will be out of energy, they simply go and collapse with the nucleus. But that is not happening actually. So that's why the model got failed. Further, if we go further in the limitations, further according to the classical electromagnetic theory, frequency of electromagnetic waves emitted by a revolving electron must be equals to the frequency of revolution of electron. As the revolving electrons spiral inwards, their angular velocities and hence their frequencies of revolution would change continuously. Okay. Therefore, frequency of electromagnetic waves emitted must change continuously, but they are not. Therefore, atoms should emit continuous spectrum, but what we observe is only a line spectrum. So that is the another limitations of Rutherford atomic model. Now, what is the Bohr atomic model? So basically, it is also known as Bohr model of hydrogen atom. Okay. So in the view of the limitation of Rutherford atomic model, Niels Bohr, he came to the conclusion that classical mechanics and electromagnetism could not be applied to the processes on the atomic scale. So he observed the Rutherford's model and limitations of it. Then he concluded that the two concepts that we used while putting a limitation on the Rutherford atomic model, the classical mechanics and the another one is electromagnetism. These two actually could not be applied to the processes when we talk about the atomic scale. First thing, he did this. Bohr cleverly combined the classical ideas and early quantum concept that were given by Max Planck's quantum theory, okay, to give what is now known as Bohr model of hydrogen atom. Following are the three basic postulates of this model that he gave. First, every atom consists of a central core which we call nucleus, in which entire positive charge and almost entire mass of the atom are concentrated. So the previous thing of Rutherford model is actually being carried forward here. Central core, where the entire positive charge is there and entire mass is there. Previously the similar thing happened. Okay. A suitable number of electrons having as much negative charge as the positive charge on the nucleus revolve around the nucleus in circular orbits. The centripetal force required for revolution is provided by the electrostatic force of attraction that is between the electron and the nucleus. So he said that the centripetal force that we require to make the electron revolve around the nucleus is actually provided by the electrostatic force of attraction that is between the electron and the nucleus. This postulate stresses that an electron in an atom could revolve in certain stable orbits only without the emission of radiant energy. So why the electron is not losing the energy and going to collapse with the nucleus? Because the electron is revolving in the certain stable orbits and not radiating energy. Thus, each atom exists only in certain definite stable states with definite total energy. These are called stationary states of the atom. So that's why the atom is stable. Bohr's second postulates define the stable orbits. According to Bohr, electron could revolve only in certain discrete non-radiating orbits that we call as the stationary orbits, for which the total angular momentum of the revolving electron is actually an integral multiple of h by 2 pi, where h is actually the Planck's constant. Thus, the angular momentum of the orbiting electron is quantized as angular momentum of the electron equals to mvr. For any permitted or stationary orbit, mvr equals to pi h by 2 pi, where n is any positive integer. We could take any 1, 2, 3, so on. It is called what we call as a principal quantum number. The quantum condition limits the number of allowed orbits. The electron, while revolving in such orbits, shall not lose energy. Therefore, its energy would stay constant. Third postulate is the emission absorption of energy occurs only when an electron jumps from one of its specified non-rotating orbit to another. The difference in the total energy of electron in the two permitted orbits is observed when the electron jumps from inner to the outer orbit and emitted when electron jumps from outer to the inner orbit. So absorption in case when electron jumping from inner to outer. Emission is the case when electron jumping from outer to inner. If E1 is total energy of electron in an inner stationary orbit and E2 is its total energy in an outer stationary orbit, then the frequency of V, radiation emitted on jumping from outer to inner orbit, is actually represented by or given by whatever you want to call it. You can call it, it's your call, by HV equals to E2 minus E1. That's it. Now, De-Brogile explanation of Bohr's second postulate of quantization. Like we know, in the second postulate of Bohr, he discussed about the quantization. Okay, so De-Brogile actually gives the explanation of the second postulate of quantization. Like what do we mean by exactly of it? So according to the De-Broglie, the electron in its circular orbit, as proposed by Bohr, must be seen as a particle wave. Hence, according to De-Broglie, a stationary orbit is that which contains an integral number of de Broglie waves that are associated with the revolving electron. Angular momentum of electron revolving in nth orbit must be an integral multiple of h by 2 pi, which is the quantum condition that is proposed by Bohr in the second postulate. Thus, the wave-particle duality plays the central role in the structure of the atom. Now, what are the limitations of Bohr theory? How the Bohr theory got rejected on certain grounds? So, following are some of the limitations of Bohr's theory. First, this theory is applicable only to the simplest atom like hydrogen with Z equals to 1. This theory fails in case of atoms of other elements for which Z is greater than 1. The theory does not explain why orbits of electrons actually taken as circular, while elliptical orbits are also possible. Third is, Bohr's theory does not explain the fine structure of spectral lines even in the hydrogen atom. Bohr's theory does not say anything about the relative intensities of spectral lines. Bohr's theory does not take into account the wave properties of electrons. Now, excitation and ionization potential. Whenever an electron which is revolving in a stationary orbit of an atom absorbs some energy, the two things may occur on that time. First, the electron may jump from outer orbit of energy. Okay, there is a mistake. The electron may jump over to an outer orbit of higher energy. First case. Second, this is the explanation of this. This process in which absorption of energy by an electron takes the electron from an inner orbit to some outer orbit of higher energy, that is what we call as excitation. So excitation is a case when the electron may jump over to an outer orbit of higher energy. Okay. The atom is said to be in the excited state. That's why he came out. Okay, excited state means when the atom actually came out. Here you can see like this. Okay. The minimum oscillating potential which provides an electron energy sufficient in order to jump from the innermost orbit, ground state, to one of the outer orbits is what we call excitation potential or resonance potential. Excitation potential of an atom is not one. It could have many values depending on the state to which the atom is excited. Second is, if the energy supplied is so large that it could remove an electron from the outermost orbit of an atom, this process is called ionization. Thus, the ionization is the phenomenon of removal of an electron from the outermost orbit of an atom. The minimum oscillating potential which would provide an electron energy sufficient thus to remove it from the atom is what we call as the ionization potential. Note that for a given element, ionization potential is actually fixed. But for different elements, ionization potentials are different. Now, what are some important facts about atoms? First, just as dots of light of only 3 colors combine to form almost every conceivable color on TV screen, only about 100 distinct kinds of atoms combine to form all the materials in this universe. Okay, like 3 colors we know, primary colors, red, blue and green. These could be combined to form any almost conceivable color on TV screen. That's how only the 100 distinct kinds of atoms could be combined to form almost all the materials in this universe. We are all made up of the same kind of atoms. Their atom cycle from person to person as we breathe and our precipitation is vaporized. Thereafter, atoms are thus recyclable. Our brain may be made of atoms that were once part of Albert Einstein and Charlie Chaplin. An orbit of an electron in the Bohr's model in the circular path of motion of an electron around the nucleus. But according to the quantum mechanics, we couldn't associate a definite part with the motion of electrons in an atom. So we could only talk about the probability of finding an electron in a certain region of space around the nucleus. This probability is inferred from one electron, which may function called the orbital. This orbital having no resemblance whatsoever with the orbit. Thereafter, the nuclear forces. So, the nuclear force are actually of two types, the strong nuclear force and the weak nuclear force. First of all, what we really require to understand is what do we mean by the nuclear force. So nuclear force, actually the strong forces of attraction which holding together the nucleons. Nucleons is a term we use to represent the two things, neutrons and protons, in the tiny nucleus of an atom, which having the radius of 10 power minus 15 m. In spite of strong electrostatic forces or repulsion between the protons, these forces are actually very complex in nature. Some of the important characteristics of these forces that we could go through are, first, nuclear forces act between a pair of neutrons, a pair of protons, and also between a neutron-proton pair with the same strength. This shows that the nuclear force is actually independent of charge. Nuclear force is also the strongest forces in the nature. The magnitude of nuclear forces is actually 100 times that of electrostatic forces and 10 power 38 times that of the gravitational forces between the nucleons. Because we know gravitational force is the weakest force of the nature. Okay, so that's why in comparison with this, the nuclear forces is 10 power 38 times more stronger. Then that is why the nucleus are held together in the nucleus in spite of electrostatic force or repulsion between the protons. The nuclear forces are very short range forces. They are operative up to a distance of the order of few Fermi only. The variation of nuclear forces with the distance between the nucleons is not known exactly. Nuclear forces negligible when distance between nucleons is more than 10 Fermi. So we could say that these are the short range forces only. So they could be operative or affected only up to 10 Fermi. If the distance grows larger than the 10 Fermi, these forces will become ineffective or inoperative. When nucleons are brought closer, the nuclear force of attraction develops, which goes on increasing rapidly with decreasing distance. However, nuclear forces do not obey inverse square law when distance between nucleons become less than 0.5 Fermi. The nuclear forces become strongly repulsive in this situation. Each nucleon interacts with its immediate neighbors only, rather than with all the other nucleons in the nucleus. The nuclear forces are independent on spin or angular momentum of nuclei. Nuclear forces are also the non-central forces. This shows that the distribution of nucleons in a nucleus is not spherically symmetric as we generally conceived. Nuclear forces, strongest attractive forces between the nucleons which are independent of the charge, but these are short range. These are also non-central. These are also non-conservative, and even they are not obeying inverse square law. So now let's have a talk. What is the nature of nuclear force? So there was a Japanese physicist whose name was Yukawa. He postulated in the year 1936 that nuclear forces between the nucleons actually arises on account of continuous exchange of particles called mesons between the nucleons. Later on, these particles were detected experimentally. They were found to having a mass about 270 times the mass of an electron. Three types of mesons were detected. Mesons carrying no charge were called neutral pi mesons, pi degree. Mesons carrying unit positive charge, which were called positive pi meson, like pi plus, and mesons carrying the unit negative charge, each were called negative pi meson, meson negative. Sorry, pi negative. According to Meson's theory or Yukawa theory of nuclear forces, all nucleons consist of identical cores surrounded by a pulsating cloud of pi meson. Meson may be neutral, pi 0, or carry either charge, may be pi positive or pi negative. The difference between a proton and a neutron is essentially in the composition of their respective meson clouds. The force between the neutron and proton is due to the exchange of charge meson between them. Therefore, P plus pi minus equals to N0, or N0 plus pi plus equals to P plus. Thus, proton and neutron continuously exchange their nature by absorbing and emitting the pi mesons. Thus, N0 equals to P plus pi minus and P plus equals to N0 plus pi plus. Anything could be there. The forces between a pair of neutrons or a pair of protons are the result of the exchange of neutral meson pi 0 between them. Therefore, P equals to P1 plus pi neutral or P plus pi neutral equals to P1, and N equals to N plus pi neutral or N plus pi neutral equals to N1. In both the cases, a proton or a neutron is actually converted into a new state after emitting or absorbing the pi neutral meson. Thus, exchange of pi meson between nucleons keeps the nucleons bound together. It is responsible for the nuclear forces. Now, nuclear stability depends on the factors. Let's see them. The stability of nucleus is determined by the value of its binding energy per nucleon. Higher the binding energy or nucleon, more stable in the nucleus. The stability of a nucleus also determined by its neutron to proton ratio. Light nuclei stable only if they contain about the same number of protons and neutrons. If any of them is higher, that will become unstable. Heavy nuclei, on the other hand, actually stable only when they have more neutrons than protons. Thus, heavy nuclei are neutron rich compared to the lighter nuclei. This is as if neutrons help to stabilize a nucleus. Then, third is the stability of the nuclide is also determined by the constitution whether it contains an even or odd number of protons and neutrons. A detailed study shows that the stable nuclei often contain the even number of protons or neutrons or both. There is a note that there are 103 different elements. It means 103 different elements, including the transuranic elements. Z equals to 1 is hydrogen and Z. 103rd is lawrencium. All these elements having isotopes, and as such there are 100 different nuclides. Out of these, 280 are stable and the rest are unstable. Then what is the radioactivity? Radioactivity is the property by virtue of which an element disintegrates itself without being forced by any external agent to do so. The phenomenon was discovered by French physicist Henri Becquerel in 1896. He observed that the uranium salts possessed a peculiar property of affecting a photographic plate even when the plate was in the light-proof package. He thought must be due to the certain active radiations emitted by uranium salts. These radiations were also called as Becquerel rays. This phenomenon of emission of active radiations by an element was termed radioactivity later on. The elements exhibiting this property were called the radioactive elements. The total number of radioactive elements known at present is about 40. For instance, natural elements with atomic number greater than 82 are all radioactive elements. Their nuclei is thus unstable nuclei. Some examples are radium, thorium, actinium, polonium, etc. The experimental evidence reveals that the phenomenon of radioactivity is not at all affected by the imposed conditions of temperature, pressure, chemical combination, etc. Therefore, electrons orbiting the nucleus were not responsible for radioactivity. Hence, the radioactivity must be property of heavy nuclei only. So with this, we have finished this lecture. It is requested and advisable to all of you kindly revise the facts and figures at all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.